Here is an example of using the moment generating function to generate moments. Use the moment generating function to find the expected value of x, the expected value of x squared, and the expected value of x cubed for the continuous random variable x with probability density function f of x is equal to e to the minus x on the support x greater than 0. So the first thing that's going to be done here is to find the moment generating function of x, and that is m of t, by definition, is the expected value of e to the t times x. Now you know that that e to the t times x is going to show up right here, and so you will have the integral from 0 to infinity, that is the support of the random variable x, of e to the tx times the probability density function e to the minus x dx. Now here you have like base, so you can add the exponents, and in addition you can factor out an x, so you get e to the t minus 1 times x dx. Think for a minute about this integrand. If it is e to the, let's say, positive 3 times x, this integral is going to diverge. On the other hand, if it is e to the minus 3 times x, then the integral will converge. So from that, we have to throw in the assumption that t minus 1, which is this coefficient out front of x, has to be negative. Now you'll see in a minute why this comes into play, but it is an important detail, and part of getting moment generating functions right is to get all the details right. So if this is indeed the case that we have an integral that does converge, you now can take and multiply inside the integral by t minus 1, multiply outside the integral by 1 over t minus 1, and this integral becomes e to the t minus 1 times x, evaluated between the limits 0 to infinity. When you plug in infinity and make this assumption, e to the minus some negative number times infinity will give you 0. And when you plug in 0, you get e to the 0, which is 1. So you get 0 minus 1, which is negative 1, and that negates this, so we get 1 over 1 minus t as the moment generating function. Now, one more thing to notice, this t minus 1 is less than 0 is the same as saying t is less than 1 if you add both 1 to both sides of that inequality. And I'm going to draw an axis here with t, and I'm going to put 0 right here, and here is 1. So our moment generating function is defined for all t values which are less than 1. If you go back to the definition of a moment generating function, and in fact I think I'll go back to that definition, you notice that we had to be defined on some interval between negative h and positive h. If that's the case, then we have a moment generating function. So back to this problem, we can pick any h we want. It looks like the way I've drawn it here is I've got an h of about maybe 1/3 or so. It is defined in that neighborhood of 0, and because of that, this is a legitimate moment generating function. Now, once we have the moment generating function 1 over 1 minus t, I'll go ahead and write that up top here. And again, don't forget to write where it is defined. You can take 3 derivatives of this. Here is the first derivative of that function, and here is the second derivative of that function, and here is the third derivative of that function. Then using our theorem, we plug in t equals 0. When you plug in t equals 0 to here, you get a 1. Plug in t equals 0 here, you get 2. Plug in t equals 0 here, and you get 6. This is the expected value of x, expected value of x squared, and expected value of x cubed, and that's how you use a moment generating function. Notice if you wanted to calculate this expected value of x cubed in the usual fashion, you would integrate over the support of x cubed times the probability density function dx. And this is a big pain because you've got to use integration by parts 3 times over, lots of opportunities for errors, whereas this one generates all 3 of the moments very quickly by just plugging t equals 0 into the derivatives.